Hi, can you see my slides okay?
Yes.
Yeah, great. Thanks very much. Thanks, Hannah. Hi, my name's Heather Doig. I'm studying a Masters of Data Science at the University of Sydney. Today I'll be presenting our research on unsupervised clustering of benthic images using autoencoders that have been trained using adversarial and generative methods. I completed this research at the Australian Centre for Field Robotics at Sydney Uni with the assistance and guidance of Oscar, Howe and Stefan. So today I'll be covering these areas. Firstly, the challenge of managing large data sets of seafloor or benthic images. Next, how autoencoders can be used to perform unsupervised clustering into habitat classes. I'll talk about the generative and adversarial training methods that we used in this research, and then I'll take you through the data set that we applied our approach to and our results using these methods. Covering 70% of the Earth's surface, our oceans play an important role in our economy and environment. The last few decades have seen an increase in robotic platforms, both on the surface and underwater, to help us observe and monitor the ocean environment. Large numbers of high-resolution images of the seafloor are being collected, but processing this data in a timely and low-cost fashion continues to be a challenge. This research aimed at applying an existing method for clustering images without human intervention into semantically similar groups. Autoencoders have been used successfully for unsupervised clustering of images in other domains, and this would provide a low-cost method to analyse benthic images without human intervention. An autoencoder is a mathematical model that encodes an input like an image into a smaller latent variable and then decodes the variable back into a reconstruction of the original image. The low-dimension latent variable generated by the encoder tends to locate semantically similar examples together. The latent variable can then be used as an input for a Gaussian mixture model, which clusters the images into a specified number of habitat classes. The autoencoder is a trained deep neural network. This slide shows the architecture of the encoder. The decoder uses the same architecture, but in reverse to reconstruct the image. The encoder starts with a 128 by 128 image, followed by 4 convolutional layers and then a fully connected layer to encode the latent variable. The training methods for the autoencoder network were varied while keeping the autoencoder architecture and the clustering model the same. 3 variations of autoencoder training were used, as well as training with and without noise added to the input image. Denoising or adding noise to the input can improve the ability of the autoencoder to reconstruct the image. So the first of the 3 types of training used was just a basic autoencoder. The input image, shown here as X, is passed through the encoder to create the latent variable Z hat, and then this is decoded to reconstruct the image X tilde. The network is trained by minimising the binary cross-entropy loss between the original and the reconstructed image. The next variation in training was an adversarial autoencoder. Adversarial training introduces a discriminator, shown here as DZ, which is added to the basic autoencoder network. ZBatch is a fake latent variable. It's randomly generated with a Gaussian distribution. The discriminator is trained to identify fake latent variables. So ZBatch should be detected to be a fake, whereas Z hat that was encoded from a real image should be detected as genuine. In addition to the image reconstruction loss from the basic autoencoder, there is an additional discriminator loss term. Training the encoder and the discriminator are alternated in a minimax game with the encoder trying to minimise the discriminator loss while the discriminator tries to maximise it. The reconstruction loss and discriminator loss are summed using a weighting variable to give one loss term for the whole network. The third and final method used was based on work by Connor Lazaru in 2020 called an autoencoding generative adversarial network, or AE-GAN. This method was based on cycle GAN and aimed to use latent variables to transition smoothly from one image to another, so such as from a winter scene of a landscape to a summer scene. For our task of clustering images, it was hoped that this training method could improve the information captured by the latent variable and therefore improve the clustering. This then gets a little bit complicated, but this was the most interesting part of my work. It starts with the basic autoencoder and the image reconstruction loss. And then there is the latent variable discriminator and its discriminator loss. Then we start to add in the cyclical nature of the network. Just like the image converted to a latent variable and then reconstructed back into an image, the same thing happens with Z-batch. Z-batch is the randomly generated latent variable, and Z-batch is passed into the decoder to construct an image, which is then encoded to reconstruct Z-batch. This adds a new reconstruction loss that finds the difference between the original Z-batch and the reconstructed Z-batch. Finally, an additional image discriminator, DX, is added to the network to detect the original images. The discriminator is trained to find reconstructed images or images created from Z-batch to be false, while an original image is true. This also has its own loss term. The minimax training of the discriminators is now training both the encoder and the decoder. There are now 4 loss terms, which are summed using weighting variables. So in Lazarou's work, this network produced results that could smoothly transition from one image to another by linearly interpolating new latent variables between the original and the final image. So to test the effectiveness of this autoencoder model and training methods, we applied it to a data set of benthic images that were captured by the AUV Sirius at the O'Hara Reef in Tasmania in 2008. The trajectory of the 2 surveys are shown here. The transect survey has annotations with 8 habitat classes, allowing a comparison of results with a ground truth. The autoencoder was trained on the one-line data set shown in blue using 6,500 images. 80% of the images were randomly selected for training, with the remaining 20% used as a validation set. Overall, the results were good, with the adversarial autoencoders giving the best performance. These examples are from the adversarial autoencoder with no noise added during training. It shows example images from each of the 6 habitat classes. Visually, the images in the same row can be seen to be comparable to each other. The classes have then been plotted against the trajectory of the survey. The top row shows the kelp habitat found at the start of the survey in the shallower regions. The bottom 2 rows show screw shell followed by sand, and this corresponds well to the screw shell which is found in deeper regions and then followed by sand as it then moves back up into the reef. Clustering performance measures were used to give a quantitative indication of the clustering quality. The silhouette coefficient, the Kalinsky-Harabaz index and the Davies-Boulden index were used. And the best results are shown here in bold, with a higher silhouette coefficient and CHI and a lower DBI indicating better clustering. The GAN AE with Gaussian noise actually gave the worst performance. The results for the transect survey were also good, with the adversarial autoencoders producing the best performance. The example images for each class have been ordered by average depth. They appear to show similar habitats, particularly at the top classes and in the bottom classes, but then it's harder to distinguish when it comes into the different reef areas. The transect survey data had been annotated by experts with labels of 8 habitat classes, allowing a comparison of classes to ground truth. In addition to the previous clustering measures, adjusted RAND index and adjusted mutual information have been used to measure against the ground truth labels. The adversarial autoencoder with and without Gaussian noise produced the best results. It's also worth noting that the GAN with Gaussian noise, this bottom one, has noticeably lower performance when compared to the basic autoencoder. It had been hoped that the cyclical training using the additional discriminator and lost terms would improve the information captured by the latent variable and therefore the clustering, but this does not appear to be the case. Overall, the research showed that the autoencoder using adversarial training produced good quality results in unsupervised clustering. Unfortunately, the GAN autoencoder did not produce better results and actually seemed to perform worse than the basic autoencoder when noise was added. GANs can be difficult to train, and there are also many parameters to tune, including the weighting of the different losses. It would be worth investigating whether the GAN autoencoder results could be improved upon by tuning the parameters and revisiting the minimax training method. Thanks very much for your time.
Thank you. So do that. Okay, so any questions? So I'm checking the channels and the Slack. So if not, I have a question. Okay, so there is one question from Scarlett Rain. Thanks for a great presentation. How are the loss weighting terms determined for the GAN architecture?
Sorry, so could you say that again? How
are the loss weighting terms determined for the GAN architecture?
So I used some initial weightings used by Lazar in his work, and then one of the terms I did reduce. So sorry, I'd have to refer to the paper, but I did just reduce one of the terms. So I think there's quite a lot of potential to actually tune all of those weightings, but running the GAN AE actually took about sort of 2 to 3 times longer than the basic autoencoder. So it's quite a time-consuming process to tune those parameters.
Okay. So in the meantime, while we are waiting for if there's other questions, I'm actually curious. Do you have any insight on that bad performance of the GAN plus the Gaussian? Because it seems, I mean, if you, for instance, change the distribution, does that work a little bit better, or is it really just it's problematic when you start having the noise in there?
Yeah, I was surprised that the noise made it sort of dropped the performance quite so much. I wonder if either I could reduce the learning rate and tune and run it for more epochs. So I actually just ran it for the same epochs for all the different training methods. So it may just need more time and smaller increments to find a better result.